Okay, so now we're going to look at some higher order differential equations. So a lot of people would think about this and say this has nothing to do with linear algebra. Oh, it really does. So let's just start. Let's say we had y to the fifth derivative plus, let's say, 4y to the fourth. And let's say minus 7y prime 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 plus 12y prime prime. Let's say 8y prime, and then let's say plus y. Okay. Now, a lot of y'all are going to look at this and say, this is not linear algebra. This has nothing to do with matrices. How does this even look anything remotely like a matrix? Huh. Let's see if we can't play with that. First thing I'm going to do is I'm going to move all the derivatives, except the fifth one, to the other side. Okay, so well, it still doesn't look like a matrix. Okay? Let's see, how can I form this into a matrix and examine its eigenvalues and eigenvectors and all that good stuff? Well, let's do it like this. Okay. So in class last time we were talking about systems of equations. So you'd have an x1, x2 prime equals some matrix, which is a fundamental matrix multiplied by x1, x2. We're going to try to set this up in a very similar way. So, on one side of the problem, I'm going to have a prime. Okay? Let's speed this up a little bit. So y prime, y prime prime, y prime prime prime, and then y to the fourth derivative. It's going to have a prime on it. Okay. Now this is going to have to equal some type of matrix. Okay. Multiplied by y prime, y prime prime. Okay. Now think about this. If I take the derivative of this side of the problem, what is this guy right here, this last one? The derivative is up there. It's going to be applied to this thing right here. So this is really the fifth derivative. Okay? So since this is the fifth derivative, we're going to use this equation right here as the bottom row. Okay? See if I can put these both on the same page. Yeah. Okay. Okay. So the fifth derivative equals, right, so that would be negative 1, negative 8, negative 12, and then 7, and negative 4. Okay? So that's that equation up there. All right. Now I got to think about what am I going to put in all of this extra stuff to fill this in and make this a complete matrix. Okay, so how many do I have? 1, 2, 3, 4, 5. Okay. All right. Okay, so that's the offset diagonal matrix, right? Okay, so think about what is this matrix actually telling us? So this first term right here, this first row, this is going to become a y prime, right? So when 0, 1, 0, 0 acts upon this, the 0, 1, it's going to hit y prime, okay? So that first line, what is it really saying? Okay, y prime equals y prime. The second line says y prime prime equals y prime prime. And the next one says y prime 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 equals y prime prime prime. And the last one says y to the fourth equals y to the fourth. Okay? And then the very last line, that is the one that is down below everybody, is that y to the fifth equals negative y times 8y prime minus 12y prime prime plus 7y prime 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 minus 4y to the fourth. Okay. So this is how you can set up any higher order differential equation into a matrix, okay? And this, this one would be very hard to solve. Because think about what the auxiliary equation for this thing would be. It would be a 5th degree polynomial. And whenever you take the determinant of a minus lambda I, and you look for the eigenvalues of this matrix, what are the eigenvalues of this matrix going to be? They're going to be the roots of the auxiliary equation. Okay, so this is actually one way to, if you have a polynomial that's a very large degree polynomial, and you don't know how to solve for its roots, turn it into this and tell the computer to do it for you.